Hello, good morning, good afternoon, and good evening, everybody, wherever you are. My name is Alessandro Piglia. I am the managing partner of Kairos 3D, and I'm here today with Luca Vezzadini, co-founder and chief technology officer of Kairos, to introduce you to our Kairos Gilgamesh 4.0 software platform. Basically, technology for agnostic 3D digital twins for connected operations. So a couple of words about our company. Kairos 3D is a cutting-edge real-time 3D software company based in Torino, Italy. Our only focus is 3D digital twin for the industrial market, and we have developed our own software platform for this purpose, which is called Gilgamesh. Basically, as I said, we have a specific focus on the industrial market, and we drive our product roadmap toward this specific segment, collecting feedback from our user base, of course. The product strategy that we have is trying to be as much agnostic as possible in terms of external systems interoperability and in terms of capability to load any kind of 3D CAD model, any format, any size, and transform it very quickly and with little effort into a highly intelligent, interoperable 3D digital twin. From the business perspective side, we have an industrial partner ecosystem for business development and for our sales strategy. And also, we have a partner ecosystem on the project delivery side. So what is a digital twin? Basically, a digital twin is a comprehensive asset awareness tool. So it is a virtual representation of a physical asset capable of replicating its physical appearance and also its current operating processes and its current or predicted performance. So basically, a digital twin has two categories, the plant twin and the process twin. The plant twin is the representation or the physical model of the asset, while the process twin refers to the modeled behavior or to the actual performance of the asset, depending if you are in a simulation mode or if you are connected to the real data coming from the asset itself. Our platform offers means to easily create immersive plant twin and to seamlessly connect them to all the relevant data sources. So let's see how and which are the business values that we bring to the Gilgamesh software platform. Basically, we support the full asset lifecycle from the design phase to the build phase to the operation phase. One important aspect is that during the design phase and the build phase, we do not substitute the classical tools that are employed there, like, for instance, Navisworks in the design phase for design review. Rather, we can complement those tools, adding additional values, for instance, for the smart design review phases, where the system can automatically turn CAD models into highly realistic interactive digital twins to get accurate preview of the models and to evaluate the projects against the requirements, to verify the outcomes of previous activities and identify issues before committing to further work. Furthermore, also during the design phase, we offer real-time collaboration between engineers in different offices and even on different continents. So we allow accessing diverse expertise without wasting time and money in travel. Then during the build phase, we can be used for virtual commissioning. So as a planning tool to create the standard operating procedures, and then to apply this procedure in a virtual environment, so to support the virtual commissioning of the asset. Definitely, if you have employed our technology during these phases of the asset lifecycle, basically you have been allowed to develop a roadmap for the overall digital twin integrated delivery that ends up with a great support to the operation phase. Where in fact, during the operation phase, Gilgamesh provides easy ways to give field operator training support through training. And also we provide asset health management by superimposing data coming from the plant system in real time to the 3D representation of the asset, hence providing a more holistic and comprehensive view of what's happening in the asset, of the data phenomena that are happening, providing asset owners and control room operators, asset managers, a better way to take decision and to move forward with the work. So how do we work? Basically, as I said, we are agnostic in the sense that we can load any format, any size of 3D CAD models. Once the model is loaded into our platform, immediately out of the box, it can be deployed to any device like head-mounted displays, stereoscopic screen, widescreen tablets, or immersive environment like caves, igloos. It can be connected to any kind of external source. As I mentioned, we are agnostics for interoperability with external systems, so we leverage standard technologies like the OPC protocol or the relational database technology. And we can deploy on top of the 3D representation of the asset any kind of data. The approach of Gilgamesh is starting from the loading of the model. Then there is a graphic quality upscales that has a different output option for different graphic quality level, hence different effort to deploy the digital twin. Then we offer visual tools for defining the business logic of the digital twin itself. This visual tool is called the module editor, through which you can specify the simulation scenarios, the mapping to external systems, the business logic for showing information by business priority and so forth. Note that no programming skills are required to use the editor. And then, as I said, out of the box, so without any additional effort, you can deploy the resulting digital twin to any kind of device. So please, if you want to get more insights about our platform or have a demo to yourself, get in touch with us to this address. And now I will leave to Luca for a real-time demo of our solution. Thank you very much.
Hello, everybody. Thanks, Alessandro, for the introduction. I'm now trying to show directly into the application some of the features that have been introduced in the presentation. The first thing that we start is look at an actual example, a 3D model that we've prepared. This is actually an equipment element, so it's not a complete plant. In this case, it's just a single equipment element imported from CAD, and its graphics quality has been upscaled so that it shows highly realistic features, like you will see some animations, you'll see some shadows and so on. Let me start by by moving into the 3D environment. You see that the paradigm of interaction is quite simple. So when you move around, items are highlighted in white, indicating that they can be selected, they can be operated by the user. So if I get closer to one of them, like this valve, I can click on it or I can select it. And I get basic information like its tag, some description, and maybe status information, like in this case, it's open state. Depending on the type of the selected item, I get different information and also different possible actions that I can do with it. Everything is coming, it's configured by the platform in a kind of automatic way, also when we import the CAD. Navigation cannot, in this case, it's happening, I'm using a keyboard and mouse, but we could use generic devices like gamepad. We could use, of course, depending on the specific output device. For example, if you have a head-mounted display, we use the standard controllers that I ship with them and so on. So as I was saying, I can freely move around in the environment. I have what we call collision detection. So I cannot cross objects. This is to mimic correctly what the user would do in an actual environment. Sorry. And I can also use what we call position bookmarks. So in the toolbar here, you have a menu that shows a list of predefined positions, so they can quickly move among different parts and predefined points in the 3D environment. Let me go, for example, to a place that might be interesting for some application that we will see later. So let me go down to the ground floor close to one of these item. This is a pump. So when I select a pump, I just see basic information like its tag and its description. We interface to external system, as Alessandro is introduced, to get data and link it to the 3D environment. In particular, for example, you see that we can show images in this case, or this could be pictures, it could be specifications, technical data, and so on. Of course, depending on the resolution, we can zoom in and zoom out. We have documents, for example, a data sheet, user manuals. So in this case, this is, I think, a PDF document that I can open, and this is shown directly. So this is a way to link to the context of the 3D environment, the external information. And let me close this menu. We can also, for example, see an interactive process and instrumentation diagram. In this case, you see that I've opened the PNID for this equipment element, and the system is highlighting the tag that I was starting from, so the specific pump. Note that there is a directional link in this case between the 2D information of this drawing and the 3D environment. So I can, for example, move around, select other items like this one, or any item. This is a ball valve, for example, and I can be teleported into the 3D item to that object. So you see that that is the one that was highlighted in the 3D environment. Alessandro also already mentioned the link to our external systems via, for example, the OPC protocol. So in this case, you see a transmitter that is displaying a value. This value is coming from a link that we will see later to an external simulator. So the 3D environment, to increase the realism of the simulation of the data that is displaying, can be displaying values coming from those external systems. This is useful both in training applications, for example, when you link to a simulator, but it can also show real-time data, for example, coming directly from the plant. And in this case, of course, is useful when used as a asset health monitoring system. It's important to note also that it's not mandatory to have a link to such an external system, because, for example, for training application, we could imagine scripting via our visual tool, the module editor, kind of simulation and transitions that are used to explain to the user what happens when it takes action, like when you close a valve, for example, to see transitions on this kind of indicators. Let me also show you something different for the training, for example. When we're talking about training, the user is normally supposed to run through an exercise. So he has a task list or anyway, a list of steps and action that he has to take, normally simulating an actual procedure that he would do in the real life. In this case, as we will see, we'll take a couple of steps, like the first one, which is asking us to close a valve on the oil inlet. So just to make things a bit faster, let me go directly to the oil inlet to move on for this part. So as I was saying, in this case, we are connected to an external process simulator. This is the oil inlet line for the vessel. Let me show you in the meantime the external simulator very quickly, the interface. This is the oil inlet line. The external simulator is computing what happens when any parameter changes. So what I would do now, for example, from the 3D environment, I will try to close this valve to throttle it to 20%. So this would probably cause an increase in the pressure upstream to the valve. And we will see that happening in a second. Of course, this simulator is interfaced, as Alessandro was explaining, via the OPC protocol, and all the external, all of the standard simulators normally support this, which is an industry standard. So let me show back the application. So the task is asking me to throttle this valve to less than 20%. So let me close it. I'm using the commands that appear here. See that I can place precisely the position. Let me do a mistake, for example, just to show what happens if I do not respect the parameters that are indicated. In this case, I was opening to 25%, and the system is tracking my actions and is detecting any error. This is useful for training because it allows, for example, unattended training. So there doesn't have to be a trainer close to me to check and make sure that I do the things correctly. This system is monitoring every single action. So now let me do it precisely, exactly. Okay, now the task is switched to green because I have done it correctly. Let's keep an eye on this PI. What we now see on the process indicator, which is upstream to the valve, its value is actually increasing. Let me try to show both things now if we can keep an eye also on the process simulator. So you see that the value is in sync with what is computed by the external system because there is a direct link. Let me now, I think that the next step is asking me to reopen the valve exactly. So if I open it back fully, what I expect is the pressure starts going down again. Notice, by the way, here in the simulator now it's open to 60%. When I validate my action, this is immediately updated and the pressure is recomputed and it's synchronized between the two systems. Okay, so this is just to show that the link with the external system is in real time and it's bidirectional. Whatever changes from the 3D environment can be notified to an external simulator, and any update that comes from the external system is, of course, reflected in the 3D environment. Let me now go to the next step just to show an additional feature. So I now have to locate an item, which is the pump. It's the same pump that we were looking at before. But let's make, again, a mistake. So I'm located this one. This is not the correct item, of course. We do a second mistake indicating another wrong item. So what happens when I do two errors, the system tags the task as failed so that I'm not frustrated, I will not stay blocked on my procedure. I can anyway move on. And also it proposes to show me what was the correct item. This is useful also for not frustrating the user and also showing me what would have been the correct item, the correct step, so that hopefully next time it takes the same exercise, it can do it correctly. Okay, now that we are here, let's move on to some other kinds of features. Let's switch to something different from training in terms of application. Let's talk about asset health management, for example. So let me introduce something that could be called data-driven visualization. So in this case, let me switch off interaction directly. And let's start seeing, for example, what we can do when integrated to external systems like databases. So let me show the info table and select any item. What's happening in this case, I am connected to a relational database. In this case, it's a demo database that is being extracted from a maintenance database for the different items in this scene. So any item that I select, of course, queries the database and provides the available information. Not all the items have the same number of columns, but anyway, the system is able to manage that. As you see, there are a different number of fields, like the discipline. Every item is tagged with a certain discipline. It has some kind of a criticality, maintenance activity, maintenance state, and so on. Again, we can connect to any database. So we're using standard protocols as usual, like SQL mainly. What we can do by this kind of agnostic interface is also do something more than just visualizing tables like it. Let me, for example, open the search feature. So I can search item, for example, by their tag. Okay, let me search anything that has 1701 in its name. I found the pump. I found also the local panel, which is close to it. But there is also a drum somewhere, which is the main vessel actually with the same tag. So the system allows me to query by tag, but it could also use the same properties that were displayed before and, for example, search along one of those properties. I was mentioning, for example, the discipline. Yeah, that's it. And let's say, for example, that we search for all the things that have mechanical or actually mech in there. And again, I found the pump and the main drum and the same thing. So the point of having an external database connected to the 3D environment allows us searching properties in the database and linking them, the value, the result directly to the 3D environment. While we're here, let me also show what we call the asset tree. This is a hierarchical representation of the 3D environment. It can be organized, in this case, as organized along a process logic, I would say, so the main lines. It could be organized in different ways, like business priorities or business applications. The point is that here we see the complete plant, and we can select any item here like I selected this PI, the camera, the point of view is moved and the object is highlighted so that I can keep in sync the true view. I can, for example, go back to the valve that we opened before. This is a way to quickly visualize in hierarchy, but also in the 3D environment, and put the two in relation very quickly. Keep talking about data-driven features. Let me also introduce what we call the color mapping. Color mapping is a way to use, for example, the properties that we have in the external database and apply their value as colors on the 3D environment. So, for example, to give you a concrete example, let me take again the discipline, the value that we've seen before. We have objects that are typed as instrument, others mechanical, and so on. We have defined a color mapping in which, based on the value of this property, objects will be colored in different ways, like you see here in the legend. So if I apply it to the 3D, what you're now seeing is a visual display of the values that you have in the database. I can apply the same visualization directly to the tree so that we have the same matching that you see in the same visualization, the same colors that you see in the 3D on the tree directly. We can also do something probably more interesting. So let me enable this color mapping, which is using a property called next due date. This is setting the indicating when each item is supposed to go under maintenance for the closest activity. And we have tagged it as red, in red the items that are supposed to go under maintenance in the coming 2 weeks, and orange for the next month, and so on. So in this case, what we are visualizing, and again, the visualization is data-driven because our attention and interaction is captured by the data, is driven by the priority that I see here. So the red is telling us that these two items are the most urgent one probably to investigate if I have to plan any maintenance activity. Let me also filter the tree so that I can keep my attention on the items that are in red. I see that there is another object. In this case, it's a transmitter. I can quickly fly to it. And this is another item that I know that will be undergoing maintenance quite soon. For example, this is an example that shows where I should be placed my attention if I'm planning maintenance operations. For example, I can start looking around in a 3D environment to prepare the intervention. I can start planning that. And we could even imagine having predefined exercises to actually simulate the maintenance activities that needs to be performed. Let me see if we still have a few minutes. Maybe we do. Let me remove this. Everything. Show very quickly another feature, which is a way to display alarms. So supposing that we're interfaced to another external system that is raising alarms and events, like could happen in any DCS. Again, we would be using, in this case, standard protocols like OPC alarm events. We will be receiving notifications from these external systems. In this case, for example, we have 3 alerts. One is on a valve, the other is on transmitters, and so on. Clicking on the item, I would be teleported to the corresponding tag to visualize where the alert is. And again, this is a way to be driven, and you see that also the trees are colored accordingly. It's a way to be driven by the data, and my attention in the 3D environment would be placed on the item that needs some specific attention. In case any new alarm is received by the external system, you would see that, for example, this icon is blinking. So if we open it again, you would see that there are a couple of new alerts. One is on a transmitter. This is probably a consequence of what was happening before. And same for the interface. Just to wrap up now what we've seen so far for the alarms, which is consistent with the first part of the demonstration. External systems do have a lot of information that we can link and we can embed in the 3D environment. We can link it and we can prioritize the attention of the user, especially for application in the context of asset health management, so that the 3D becomes, I would say, a user interface, a data-driven user interface that supports the user in its daily work to focalize the attention on the activities that needs to be done in priority. This is a type of application. We have seen in the beginning other possible uses like the training exercises. Everything is set up and configured, as Alessandro introduced before, via a tool, which is a visual tool, no programming is needed. And this is also a way to simply set up and maintain your digital twins. I think that the time is over, so I would conclude here. And of course, we are open for additional questions and requests in the future if you need it. Thanks, everybody.